Hello, my dear students. Now it's second lecture, second chapter, the mass action law in our solid state electronics course. Actually, in this lecture, I can say that this is one of the problem-solving lectures. What I mean in this lecture, we will reach what's called the mass action law, and this is one of the principal laws in semiconductor and electronics design for semiconductor devices and semiconductor materials. And without disclosing a secret, we can say that you can never find a unit test or you can never find a final exam without one or more question solved by the mass action. So that's why I call this lecture is somehow a problem-solving lecture. Maybe in the first lecture we were more toward concepts when we deal with the semiconductor fundamentals. Now we are more toward mathematics, more toward problem solving. Now, please permit me to show my presentation and start our second chapter. Okay, now I believe that you can now see my PowerPoint presentation for chapter number 2 with the title mass action law, as I mentioned. What I have to do now is to start operating my laser pointer and start our second chapter. Okay, I will start this chapter actually by some sort of revisioning on what we have already reached by the end of chapter 1. If you remember, in chapter 1, we deal with what's called the principal relation for Ohm's law. If you remember this relation, my dear students, this is actually one of the important relations we have reached in our chapter 1 content. So, if you remember, we reach an important relation linking the current density J with the electrical field eta. Let me now use for a while my simple whiteboard. So here is my whiteboard. If you remember, we have the relation saying that J, which is the current density, equals to Q n mu n times 8. And here, J is the current density given by ampere per meter square. Q is the unit charge of electron, which is 1.6 times 10 power negative 19. N is the number of electrons. And if you remember, we defined the number of electrons as the number of electrons. Here, the number of free electrons is the conduction band. And mu n is the mobility. And eta is the electrical field. So this is what we call the principal version of the Ohm's law, where we have something to link the current with the voltage, or in other words, to link the current density with the electrical field. Now, what we had made, or what we did after that is we investigate to some extent what is N, or we know that N is the number of free electrons in the conduction band, but let me say how we should calculate the N. And in order to calculate the N, if you remember, we use what's called the probability theory. Here we make some sort of multiplication between two different functions. The first function represents the probability to find an electron, and the second function represents the seats, or the available places, available states, what's called the density of the state of electron. If you remember the example of the probability to find students in a room in our A building. So we say that we have to multiply the number of seats available in the room times what we call the probability to find a student, or the probability to find an electron. So this was the final part, I believe, in our in chapter 1, if you remember, my dear students. So let me now return back to my presentation. Okay, and let's quickly brief what we have done in order to calculate the number of electrons in the conduction band. It was simply like that. So let me now again open my pointer and start. So if you remember, we say that we have a valency band, we have a conduction band, and we have what's called the energy gap with a certain value Eg. And there is something called Fermi level. Actually, we did not investigate more about this Fermi level. We talk about the Fermi function, which I will mention later on, but we did not investigate more about the Fermi level. Maybe in this lecture, inshallah, we are going to demonstrate what is Fermi level and why we are using this Fermi level. So this is simply the a virtual level that will be described later on. But now we have electrons in the valency band. When we have a natural thermal energy equal to 3 over 2 kT, here again T is given in Kelvin. So at room temperature, this T will tends to something like 300. So in this case, this energy will enable some electrons to move from the valency band to the conduction band. Now, this is what we call the free electrons. And the counting of such electron is will directly contribute to the term N, which is the number of electrons. And here we create what's called the hole, and we define the hole as a broken bond in the valency band. So, as a brief, we say that free electrons are only defined in the conduction band, holes are only defined in the valency band. So, in order to calculate, we say that we need two functions. The first function to demonstrate the states, the available seats. And as I just say, that electrons are only, or free electrons are only defined in the conduction band. So the states of electron, which is this green function known as Gc of E, where C here stands for conduction band. So just this green function demonstrates the available states of electrons. And as I mentioned in my previous lecture, in our course, as far as we are not dealing with the quantum principles, we will not investigate how this function has been determined. So we will consider it as a constant function with respect to energy, as you can see, demonstrating the available seats or the available states of the electrons in the conduction band. Similarly, you can see another function in the valency band that also demonstrates the available seats of holes. Again, this function is only defined in the valency band because holes are only defined in the valency band. Then the next step is to find the probability function. This probability function, the green probability function, which is f of E, the Fermi-Dirac function, if you remember, we already also investigated graphically and mathematically in the previous lecture. And we say that this function says that there is a small probability to find some electrons in the conduction band. However, most of the electrons are in the valency band, and actually this is somehow agreed with this schematic. As you can see, most of the electrons are bounded in the valency band. Only few amount of the electron will transfer from the valency band to the conduction band due to the thermal energy. So, as you can see here, this few amount of electrons now here is in the conduction band. And in order to determine the probability for a hole, it's simply 1 minus f of E, because if there is a probability x to find an electron, then simply the probability to find the hole equals 1 minus x. So by multiplying these two functions together, then we will have the number of electrons n in the conduction band and the number of holes p in the valency band. Logically speaking, as you know, number of electrons equals to number of holes, because for each electron excited from the valency band and it reaches the conduction band, a hole will be created. So simply n should directly equals to p, which is something somehow logical. So we call such electrons, or such, here I will transfer my terminology from using the word electron to using the word carrier. And this is very important, my dear students, because when we're talking about electron is just one type of carriers. But now, based on the definition of hole, we have another type of carriers, which is holes. So whenever I say carrier, from the word carrier, this is something that is capable to move. So we are talking about free particle, and here we are talking about either electrons in the conduction band or holes in the valency band. Both are carriers. Those carriers automatically excited from the valency band to the conduction band due to the thermal energy without any external sources, we will call them as an intrinsic carrier concentration. So what is intrinsic carrier concentration? Is simply these electrons that has been excited from the valency band to the conduction band due to the existence of a natural thermal energy called 3/2kT. Here, for example, we have, here, for example, we have 10, 20, 30, 40, 100 million, billion, 10 power 5, 10 power 7, 10 power 8, whatever the number is. This will differ from one material to another. But these electrons are those electrons who can naturally jump from the valency band to the conduction band. So this is a very important definition, my dear students, and is that we call this as an intrinsic carrier concentration. Again, very simple. Due to the symmetry of the structure, the number of electrons in the conduction band, we call it Ni, and the number of, N node, and the number of holes in the valency band, we will call it P node. So simply, N node should equal to P node, because as I mentioned, for each electron excited from the valency band to the conduction band, a hole will be created. So simply, N node is equals to P node. And now, we will call either N or P, because both are equal, we will call them Ni, or the intrinsic concentration. So again, the intrinsic concentration, this is a very important definition, is the number of carriers, I mean electrons or holes, that turns to be free due to the natural thermal action. Now, N node equal P node equal Ni. That's perfect. So I can say simply that N node times P node equals to Ni squared. We will call this a mass action law. As you can see, it's very simple. N node equal Ni, P node equal Pi, so equal Ni, sorry. So N node times P node simply equals to Ni squared, which is the mass action law. Few slides later, and we will see how this mass action law is very important in our electronics or in our semiconductor devices. So now this is the mass action law. Again, this is a very simple multiplication, but again, we have now to turn to define what I previously mentioned in my first slide in this lecture, which is this reddish line called Fermi level. What is this Fermi level? Okay, as you can see here, we're still defining this strange Fermi level, and here mathematically, this Fermi level is the point at which the probability to find an electron equals to the probability to find an hole. Because if you remember, this green curve represents the probability to find an electron, and this red curve represents the probability to find a hole. And at a certain point, these two curves overlap. Simply, if you are searching about two parameters, then they will be equal when the probability will be 50%. Very, very logical. So now at this point, which this now is the mathematical version of Fermi level, is the level at which the probability to find an electron equals to 50%. Very simple. But maybe one of you ask a very important question here. Actually, this Fermi level is against what we understand, because this Fermi level is located in what's called the forbidden gap, in the energy gap. And based on our understanding, electrons can exist either in the valency band or in the conduction band. And they should not, there should be no electron in the forbidden gap or in the energy gap. 100% true. But if you remember my previous lecture example, here is the answer. Okay, mathematically, at this point where I'm directing my pointer, at this point, the probability to find an electron equal to 50%. This is true mathematically. However, in order to determine the number of electrons, you have to multiply this probability with the density of states, with the number of states. Here, when you're going to multiply this probability with the density of states, you will find that the multiplication will be equals to 0 because simply there is no seats, there is no states. If you remember in my previous lecture, I told you, what if I told you that what is the probability to find an electron on to find the students on Monday on room 403 in building A? So on Monday, of course, there is some students. However, in room 4, there is no room code 403. So the number of seats is equal to 0. So simply, this multiplication can be equal to 0 in two cases. Either there is no seats or there is no probability. The case where there is no probability, if you remember, is the case where we are at 0 Kelvin. If you remember, at 0 Kelvin, this green curve tends to be something like a right-angled triangle, so something like that, that, and that. So here, the probability to find an electron is equal to 0 at 0 Kelvin. So you have seats, but there is no electron because the probability is equal to 0. This is, if you remember, the Friday example. When I told you what is the probability to find a student on Friday morning. It's a day off. So the seats exist, but there is no students because it's a day off. No probability to find students. But on the other case, it may be there is a probability, however, there is no seats, which is the case for Fermi 11. And then there is no electrons or no holes. So now we should agree that at Fermi 11 mathematically is the level at which the probability to find an electron equals to the probability to find a hole equals to 50%. Very simple. And it's located in the forbidden gap. And we shouldn't be somehow angry with that because the seats are equal to 0. So simply the multiplication will output 0. So this is a Fermi level. This is the physical meaning of the Fermi level. That's the mathematical meaning of the Fermi level. Let's go deeply more mathematics, and then I will also try to describe for you what is the physical meaning of the Fermi level, which is actually much more important than the mathematical. But let's now go and do it mathematically. If you remember, my dear students, in the end of the previous lecture, I told you that we also can write what's called the integral form for finding n and p, if you remember. And even I told you that I maybe ask you about writing the integral form without solving the integration. So, for example, to find an electron, the relation is very easy. Here we make an integration from EC to infinity. The integration is from EC to infinity because electrons are only defined in the conduction band. So we only limit our integration from EC to infinity. So it's an integration from EC to infinity. G of E, which simply represents the probability, or not, sorry, I'm sorry, it represents the number of seats. That's the density of states, multiplied by F of E, which is the probability to find an electron. So this formula is given. As I told you previously, we are not going to investigate how this formula is calculated because this is a quantum output. And then we already, if you remember, described this lecture as this formula somehow in details in the previous lecture, which is the Fermi-Dirac function, and we observe why it's a function in energy and why it's a function in temperature. So this is simply the integral form. You are not asked to do the integration by yourself. And then you can use the final answer directly. And in the exam, this final answer will be given to you in a form of a given in the question or in form of formulation. So this is the output. So n simply equals to 2 times 2 pi. Here is the M effective. Don't forget the effective mass. K is a Boltzmann constant. T is the temperature. H is a Planck's constant. So K and H are constants. Over 3 over 2. E power EF, which is the Fermi level, minus EC over KT. So this is simply the output of the integration. The output of the integration. Again, this output is not required to be memorized by yourself, and it will be given. And in order to make this equation more and more simple, what we are going to do is simply that we will put all these constants in one term which is called NC. And if you remember, we call this NC as the effective density of states of the conduction. So this is simply NC. So now this is NC, so N is simply equal NC e power EF minus EC over KT. Very simple. Okay. Now, how we should calculate the PP? Typically, it's the same manner. Instead of using GC of E, I'm sorry, maybe in my slides I'm not so good in representing, because I should write it here GC of E, not G of E, because I should distinguish between GC of E and GV of E. JC of E is defined in the conduction band, and JV of E is defined in the valency band. So here is this should be GC of E, and this one should be GV of E, which is the density of state in the valency band, and then this is 1 minus the Fermi energy, or the Fermi Dirac distribution, 1 minus the probability. Again, by doing the same integration, we reach a similar formula. Instead of having NC, here we have what's called NV. If you make a deep comparison or analogy between the functions, you will find that both are identical functions, except here we have the effective mass of electrons, and here we have the effective mass of holes. Maybe those students who attend our first extra session, maybe they understand more about what is the difference between the effective mass of electron and effective mass of holes. So this is the effective mass of electron, and this is the effective mass of holes. This is the only difference between NC and NV. Otherwise, all other terms are similar. And the other difference between the two formula, here we have in the exponential EF minus EC, while here we have EV minus EF. So here EV minus EF, and here EF minus EC. So these are both the both difference, and again we will call this NV the effective density of states in the valency band, as we call it here the effective density of the states in the conduction band. So simply this is the two formulas, the N and P. We already reached these formulas in the previous lecture, and as I mentioned, for maybe the third, fourth time, you don't need to memorize such formulas. It will be given for you in the exams, as in the interest or the final. So this is what about the formulas, but again, where is the formula? we are just repeating what we did in the previous lecture, but where is the formula? Actually, the answer is very simple, because as you can see here, we say that N node is equals to P node. So simply, these two formulas, this N formula and this P formula, should be equal. Yes, this N formula and this P formula should be equal. So let's now use this information in order to investigate the Fermi level. Now, let me turn for a while using my whiteboard in order to investigate the effect of the Fermi level, or how we are still in the perspective of dealing with the Fermi level or from the mathematical perspective. So now, let's now turn to the whiteboard, please, and then start investigating this one. Okay. So, as I said, we have two formulas. The first formula is for calculating N, or the number of electrons. Sorry. The first formula is calculating N, and this is equals to some constant called NC multiplied by e power EF minus EC over KT. So this is the first formula. And the second one is P, or holes, which is equals to NV exponential EV minus EF over KT. And this is the second formula. So simply, at steady state condition, this N node should be equals to this P node. As we said, N node equals to P node equals to Ni squared. Ni squared. Multiplication equals to Ni squared. So you can simply equalize these two equations. You can say that NC e power EF minus EC over KT is simply equals to NV e power EV minus EF over KT. Now you can pick up both exponential in one side and and both constants in one side. So you can say that, for example, NC over NV equals to E power EF, EV, I'm sorry, EV minus EF over KT over E power EF minus EC over KT. So this is a very simple mathematical equation. Of course, when you have two exponential dividing each other, so you can simply add a minus sign here to incorporate these two equations, these two exponentials together. So you can easily say that this is equal this minus this. So NC over NV is equals to exponential EV. Here we have minus EF and another minus EF, so minus 2EF minus EC all over KT. In order to get rid from the exponential term, it's simply you can multiply by lambda function in both sides. So you have EV minus EC minus 2EF equals to over KT, of course. I'm sorry. Equals to lambda NC over NV. Mathematically, just lambda function in both sides. So, in order to continue, I can multiply here by KT, and then it will be something like that. EV minus EC minus 2EF okay equals 2KT lambda NC or NC, yes, NC over NV. Okay, that's perfect. Again, in order to continue, you can multiply both sides by a negative sign. So you can make it like that. 2EF minus, plus EC minus EV equals to 2KT, and this negative sign will turn NC and NV, so it will become NV over NC. Okay, then 2EF equals to minus EC minus EV plus 2KT lambda NV over NC. Okay, and then you can find easily EF was half EC minus EV plus KT lambda NV over NC. Okay, now where is the information? Where is the knowledge? So please try to remember this function for 1 second, and let's now return to the presentation. Okay, so what is the term EC minus EV? If you remember, if you can see now the slide, we have the term EC minus EV. What is the term EC minus EV? So let's now again use our pointers. So, for example, this, okay, So this is the EV, this is the EC. So simply EC minus EV is the energy gap. So here, let's do it one more time. Yes, here, okay. So by equalizing these two equations together, as I just made a few seconds ago, you can easily reach an equation that say that EF equals to EC plus EV over 2 plus KT over 2 ln NC over NV. I think I have a sign error. Let me check it. I have a sign error, I think. Okay. Yes, I have a sign error here. So yes, the sign error is here. Very simple. So when I make this multiplication, this is a plus sign, not a minus sign, because here EV minus EF plus EC. So this is a plus sign, not a minus sign. And then this is a plus sign. And then after multiplying by negative, this will be turned to negative, and then this is positive. So the final form will be EF equals EC plus EV over 2 plus KT ln NV over NC. This is the final form we should reach by solving or by equalizing these two functions together. Again, where the important points are. Let's return back to our presentation. So now we have EF equals EC plus EV over 2 plus KT over 2 ln NV over NC, or NC over NV. This is the expression we have by the end of the day. What is important with this expression, or why we are considering this expression as an important expression? Okay, this is simply because let's now, or let's for a while ignore the term KT over 2 ln NC over NV. Let's ignore this term for a while. What is EC plus EV over 2? What is this? Here, this is EC, and this is EV. What if I add these together and multiply over 2? Then I'm taking the average. The average is simply something in between the EC and the EV. So it's something which is higher than EV with a distance EG over 2 and lower than EC with a distance which is EG over 2. Again, let me make it in a better manner. So when you are going to make an average between this value and this value, simply the average is something in the middle. So I'm sorry, my drawing is not so good. So let me use some sort of rubber. Okay, and let's do it one more time. Sorry. So the average will be something in the middle. So if this distance, as you can see, is called EG, then the distance between the EC is the EV and this average is simply EG over 2. And the distance between the average and the upper limit, which is EC, will be EG over 2. Very simple. So at this condition, EG over 2 and EG over 2 are equidistant from EC and EV. So the Fermi level is typically in the middle. But as you can see from the revision we have just reached, that this is not totally accurate because there is still another parameter into consideration, which is, I'm sorry, we have this parameter, this KT over 2 ln NC over NV. However, by determining the value of this parameter, because actually, as you know, NC and NV are constant, so we can easily determine this by calculating at a room temperature, we can easily determine the T, or we can easily use the T as an input to determine NC and NV, and then we can calculate this parameter. So at room temperature, we can ignore the effect of these two. And we can simply say that the Fermi level is located centrally or in the middle of the energy gap between the Fermi level, between the conduction band and the valence gap. Again, this is an approximation. This is an assumption that is not valid all the time. Here, you can ask me when this assumption may be not valid. I will tell you exactly, see the temperature. The temperature is a key parameter in this equation because here there is a temperature dependent. NC and NV are temperature dependent functions. So very logically, NC and NV are, this term is extremely or strongly dependent on temperature. Accordingly, changing the temperature may lead that this assumption is not working all the time. However, as I mentioned, in most of the cases, 99% of the cases, whenever we are working at room temperature, we can ignore this effect and we can say that simply EF equals to EC plus EV over 2, which is simply this equation. So this is the first important, or not actually the first, this is the second, because the first is the mass action law, and this is the second important equation. And before actually terminating this part or the first part of this lecture, we have to also determine another parameter. If you remember, we say that NP equals to N node 3 equals to P node equals to N node. This is the basic definition, because for each new electron we have a new hole. Accordingly, we have concluded the mass action law saying that N node times P node equals Ni squared. Very simple. So now we can easily determine Ni squared because we know N and we know P. So just by multiplying N and B, we can get Ni squared. So Ni squared equals to the N part times the P part, which is NC and V e power minus, here we make this addition, so EF has been cancelled with EF, so we have EV minus EC over KT. Now the term EV minus EC, if you remember, okay, I'm sorry, if you remember, EV minus EC is the energy gap, or EC minus EV is the energy gap, so we can here remove the term EC minus EV as minus EG over 2 KT. So this is simply Ni. Now, this is a very important observation. Ni, based on the definition we just mentioned in the beginning of this lecture, Ni is considered as the number of electrons that can leave the valency band and go to the conduction band due to the thermal energy. Perfect. Now, when I told you what is the factor that affecting this number, what is the factor that affecting the Ni, you should have a deep look to this equation, this Ni equation, and you should get the following conclusion. First, the Eg. Here you can see that Ni is function in Eg, which is actually very logical, because if this Eg is too large, then the probability to find an electron in the conduction band will be small, and then Ni will decrease. If the Eg is too small, then a lot of electrons can jump from the valency band and go to the conduction band. So logically speaking, this Ni, or the intrinsic concentration, is a function in Eg. The second important issue is the temperature. Here we call this function as a double temperature function, or double temperature dependent function. In the first look, or from the first look, you can say that, okay, Ni dependent on the temperature in this exponential form, e power minus Eg over 2 KT. Here this is the temperature. But please don't forget that NC and NV themselves are depending on temperature. So you have here two sources of temperature dependent. We have temperature dependent in NC and NV, and also you have a temperature dependent in the exponential term. The third issue is the effective mass. As you can see, that NC and NV is depending on effective mass. And as we described effective mass in the first chapter, Effective mass is the way we compensate the internal forces. And you can easily examine that by changing the material, the internal forces will change. Different materials will not have the same internal forces, or different materials will lead to different internal forces. So simply the effective mass, will change. So here we have two types of effects. What we can call the material effect. And what I mean by material here in the EG and the effective mass. Because EG, or the energy gap, is a material parameter. If you remember, we have concluded the EG from the band theory. And the effective mass is a material parameter. So if you change the material, you should expect that the Ni, or the intrinsic concentration, will change. The second issue, or the second type of parameter, is the temperature parameter. For the same material, if you change the temperature, you should expect that the Ni will also change. Here is an example for the changing of the temperature for a same material. Here, I think this is silicon. So we change the temperature for the same material, and then we examine that Ni is a strong function in temperature, as you can see. By the way, I will provide you over the e-learning with a tool that we have created in order to examine different energy gap, different Ni, different intrinsic concentration, I mean, for different materials by using this app. It's actually a mobile-based app, so you can use it either from your computer, from your mobile, everywhere you can use it. Maybe it's helpful somehow even in solving problems as well. So now this is a very another important conclusion, that Ni can vary by varying the material in the form of an effective mass of the energy gap, and by varying the temperature. Okay, so final say in this part of the second lecture, we describe Ni mathematically and physically. We now have an equation that describes the Ni, and we also know from the first slide what is Ni. We say that Ni is the amount of electrons that jump from the valency band and go to the conduction band due to the natural thermal energy in the material. So we know the physical meaning and the mathematical definition of Ni. However, for the Fermi level, we only know the mathematical meaning. We first say that the Fermi level is defined at the level at which the probability to find an electron equals to the probability to find a hole equals to 50%. And then we say that we have concluded a mathematical form for determining the position of the Fermi level. And we say that the Fermi level is located roughly in between the conduction band and the valence band, I mean in the center of the energy gap. It's not accurately in this place, but we can say that roughly it's in there. However, we're still missing that physical meaning of the Fermi level, which is actually a very important parameter in order to study the next step of this lecture, which is the doping. Here, the Fermi level is simply the indication of the ratio between electron in the conduction band and hole in the valency band. Let me describe it in a better manner. Okay, so I will turn the camera. Okay, so I believe that most of you know the traditional balance used whenever you are going to buy some sort of vegetables or foods. You see this traditional balance where you have two sets of measuring. The one of them both have these metallic plates, if you remember, and then there is two sets of measuring, and then there is some let's say bar in between, which is carrying these two blades. So when the guy there want to make the measurement, he do the following. He put some sort of bulky black calibrated mass in one side, which represents 1 kilogram, 2 kilogram, whatever. And then the fruits or the vegetables in the other side. The indications that both are equal is that this central line or this central bar is directly vertical. When this central line is directly vertical, that means that both sides are equal. Typically, it's the same here. As far as the number of electrons in the conduction band and the number of holes in the valency band are equal, then the indicator, which is the Fermi level, will be typically in the center. If the number of electrons becomes lower, so you have one side heavier than the other. If in the balance you have one side heavier than the other, then this vertical line will turn to go into the heavier side. Now, if one of the sides are greater, so if you have electrons more than holes, then Fermi level will shift upward. If you have holes greater than electron, the Fermi level will shift downward. Here you should stop me and ask, this is not possible, because as we know, for every electron coming from the valency band to the conduction band, a hole is created. So logically speaking, the number of electrons in the valency band should, the number of electrons in the conduction band should equal to the number of holes in the valency band. So logically speaking, this Fermi level should be all the time in the center of the energy gap. This is 100% true. However, in the next part, my dear students, we will deal with some conditions, with some external effects, where we can bias the number of electrons to be larger or the number of holes to be larger. This is what we call doping effect. So in the next part of our lecture, my dear students, we are going to go through the cases where we have more electron or more holes. Thank you very much, my dear students. This is the end for the first part in lecture number 2, and see you in the second part, inshallah.